Hello and welcome to General Astronomy, Lecture 16, Atmospheres of the Terrestrial Planets. We have now covered the basic ideas needed to understand the atmospheric histories of the terrestrial worlds. In this lecture, we'll use these to learn how and why each world ended up with its current atmosphere. We'll begin with the smallest worlds, the Moon and Mercury. We usually don't think of the Moon and Mercury as having atmospheres, but that does not mean that they are totally devoid of gas. However, their gas densities are far too low for sunlight to be scattered or absorbed. As a result, this lack of scattering means that even in broad daylight, you would see a pitch-black sky surrounding a bright sun. The lack of absorption means that their atmospheres do not have a troposphere, stratosphere, or thermosphere. In essence, the Moon and Mercury have only extremely low-density exospheres, without any other atmospheric layers. The total amount of gas in the exosphere of the Moon and Mercury is very small. If you could condense the entire atmospheres of either the Moon or Mercury into solid form, you would have so little material that you could almost store it in a dorm room. The low density of the gas means that collisions between atoms or molecules are in fact rare. The gas particles therefore can rise as high as their speeds allow them to, sometimes even escaping into space. As a result, the exospheres of the Moon and Mercury extend to thousands of kilometers above their surfaces. So you can see that actually in the images here on the right. These images of the atmospheres of Moon and Mercury, which are essentially exospheres only, are based on data collected with instruments sensitive to emission lines from sodium atoms. The colors represent gas density from highest, which is red, to lowest, which is blue. So you can see, these aren't actual images of the atmosphere, but it's an actual image of the Moon and Mercury, and then with this overlay showing their exospheric gases and the density from highest to lowest, which of course decreases as you move away. So that's really all there is to discuss, with regards to what their atmospheres are like, because they are almost non-existent. But this begs a pretty important question, and that's what happened to them. Well, the Moon and Mercury may once have had some gas released by volcanic outgassing, but they no longer have any volcanic activity, and any gas that was released in the distant past is now long gone. Some of the gas released long ago was probably lost through stripping by the solar wind, but it would have been lost to thermal escape anyway. Mercury cannot hold much of an atmosphere because its small size and high daytime temperature means that nearly all gas particles eventually achieve their escape velocity. The Moon is cooler than Mercury, but its size is even smaller, so it gives it a lower escape velocity, and as a result, gases escape about as easily on both worlds. The only ongoing source of gas on the Moon and Mercury is the surface ejection that occurs when micrometeorites, solar wind particles, or high-energy solar photons knock free surface atoms and molecules. This gas never accumulates because it is lost as quickly as it is gained. Some of the relatively few particles released from the surface are blasted upward fast enough to achieve escape velocity and therefore escape directly into space. There cannot be liquid water on the Moon or Mercury because the lack of significant atmospheric pressure means that water cannot remain stable in liquid form. Daytime temperatures on both worlds are generally high enough that any water ice would long ago have sublimated into gas and escaped to space. However, scientists long wondered whether water ice might reside in permanently shadowed craters near the poles, deposited by comet impacts over millions of years. For the Moon, the presence of polar ice was actually confirmed in 2009, when scientists sent the rocket from the Alcross spacecraft crashing into a crater near the South Pole. So, believe it or not, we actually purposely crashed a spacecraft into the surface of the Moon just so that we can see what kind of stuff flies up into the air afterward and analyze it for water. The debris that splashed upward revealed the presence of water vaporized from ice in the lunar soil. A radar sensor aboard one of India's spacecraft detected ice deposits in similar craters near the Moon's North Pole. More surprisingly, other missions detected small amounts of water mixed into the upper layer of lunar soil over much of the entire lunar surface. However, the origin of this water is unknown. The evidence for ice in polar craters on Mercury, however, is more limited. but scientists hope to learn more from ongoing observations by the Messenger spacecraft, which has been orbiting Mercury since 2011. So this image here on the right, it's a radar map that shows a region near the moon's north pole, imaged by a NASA instrument on one of that same India spacecraft. The green circles here represent craters in which water ice has already been detected. The ice lies at the bottom of craters that are in perpetual shadow. Shadows are not visible in this image though, since radar was used to take the image and not just a visible photograph. Moving on now to things that get a bit more interesting. Recall that Mars is only about 40% larger in radius than Mercury, but its surface reveals a much more fascinating and complex atmospheric history than that of either the Moon or Mercury. The present-day surface of Mars looks much like a desert or volcanic plain on Earth. For example, take a look at the figure on the right. However, its thin atmosphere makes Mars quite different. The low atmospheric pressure, less than about 1% of that of the Earth at the surface, explains why liquid water is unstable on the Martian surface and why visiting astronauts could not survive without a pressurized spacesuit. The atmosphere is made mostly of carbon dioxide, but the total amount of gas is so small that it creates only a weak greenhouse effect. The temperature is usually well below freezing, with a global average temperature of about negative 585 degrees Fahrenheit. The lack of oxygen means that Mars lacks an ozone layer, so much of the sun's damaging ultraviolet radiation passes unhindered to the surface. Seasonal changes lead to several major features of Martian weather. Temperatures at the winter pole drop so low to about negative 130 degrees Celsius that carbon dioxide condenses into dry ice at the winter polar cap. Meanwhile, frozen carbon dioxide at the summer pole sublimates into carbon dioxide gas, and by the peak of summer, only a residual cap of water ice remains. The atmospheric pressure therefore increases at the summer pole and decreases at the winter pole. Overall, as much as 1/3 of the total carbon dioxide of the Martian atmosphere moves seasonally between the north and the south polar caps. So we're talking about a huge majority of this carbon dioxide migrating effectively from the North Pole to South Pole, just with these seasonal changes. The strong winds associated with the cycling of carbon dioxide gas can initiate huge dust storms, particularly when the more extreme summer approaches in the southern hemisphere. At times, the Martian surface becomes almost completely obscured by airborne dust, which you can kind of see on the right in this image. As the dust settles out, it can change the surface appearance over vast areas, for example, by covering dark regions with brighter dust. Such changes fooled astronomers of the past into thinking that they were seeing seasonal changes in vegetation. Martian winds and dust storms leave Mars with perpetually dusty air, which helps to explain the colors of the Martian sky. The air on Mars is so thin that without suspended dust, the sky would be essentially black even in the daytime, just like it is on the Moon or Mercury. However, light scattered by the suspended dust tends to give the sky a yellowish-brown color, with different hues occurring with different amounts of suspended gas and whether or not it's daytime, morning, or evening. The weather on Mars does not change much from one year to the next. However, changes in its axis tilt probably cause Mars to undergo long-term cycles of climate change. Theoretical calculations suggest that Mars' axis tilt varies far more than Earth's, from as little as 0 degrees to 60 degrees or more, on timescales of hundreds of thousands to millions of years. This extreme variation arises for two reasons. First, Jupiter's gravity has a great effect on the axis of Mars, far more than it does on the Earth, because Mars's orbit is closer to Jupiter's orbit. Second, Earth's axis is stabilized by the gravity of a relatively large moon. Mars's two tiny moons, Phobos and Deimos, are far too small to offer any stabilizing influence on its axis. Changes in axis tilt affect both the severity of the seasons and the global average temperature. When Mars's axis tilt is small, the poles may stay in perpetual deep freeze for tens of thousands of years. With more carbon dioxide frozen at the poles, the atmosphere then becomes thinner, lowering the pressure and weakening the greenhouse effect. When the axis is highly tilted, the summer pole becomes much warmer, allowing substantial amounts of water ice to sublimate, along with carbon dioxide, into the atmosphere. The pressure therefore increases and Mars becomes warmer due to the strengthened greenhouse effect, although probably not enough to allow for liquid water to become stable at the surface. Changes in axis tilt may therefore destroy existing glaciers and create new ones at different latitudes. The Martian polar regions show layerings of dust and ice that probably reflects changes in climate due to the changes in axis tilt. Small changes in the tilt over the last few million years may also be responsible for the formation of the gullies that are seen on many of the crater walls today. Mars's varying axis tilt may have had important effects on its climate, but it does not explain the most dramatic climate change in Martian history: the change from a world of flowing water to the cold and dry world that we see today. The geological evidence leaves little doubt that Mars once had a wetter and warmer period, probably with rainfall, before about 3 billion years ago. The full extent of these periods is a topic of considerable scientific debate. Some scientists think that Mars may have been continuously warm and wet for much of its first billion years of existence. Others think that Mars may have had only intermediate periods of rainfall, perhaps triggered by the heat of large impacts, and that ancient lakes, ponds, or oceans may have been completely ice-covered. Either way, rain could have fallen only if temperatures were warm enough to keep water from freezing and the atmospheric pressure were high enough for liquid water to remain stable. Thus, we conclude that Mars once must have had a much thicker atmosphere with a much stronger greenhouse effect. This idea actually makes sense. Calculations suggest that Martian volcanoes should have outgassed enough carbon dioxide to make the atmosphere about 400 times as dense as it is today, and enough water to fill oceans tens or even hundreds of meters deep. Moreover, computer simulations show that if Mars had that much carbon dioxide today, its greenhouse effect would make it warm enough to allow for liquid water, and the pressure would be great enough for that water to remain stable. However, because the sun was dimmer in the distant past, even more greenhouse warming would have been needed to allow for liquid water when Mars was young. Current models are unable to account for the necessary additional warming with carbon dioxide gas alone, but additional greenhouse warming may have been provided by carbon dioxide ice clouds or atmospheric methane. The bigger question here is not whether Mars once had a denser atmosphere, though. It's what happened to it. Mars must have somehow lost most of its carbon dioxide gas. This loss would have weakened the greenhouse effect until the planet essentially froze over. Some of the carbon dioxide condensed and became part of the polar caps. Some may be chemically bound into carbonate rocks, which are rocks rich in carbon and oxygen, according to recent findings by Mars orbiters and rovers. But the bulk of the gas was probably lost to space. The precise way in which Mars lost its carbon dioxide gas is not entirely clear, but the leading hypothesis suggests a close link to a change in Mars's magnetic field. Early in its history, Mars probably had a molten, convecting metal core, much like Earth's today. The combination of this convecting metal with Mars's rotation should have been enough to produce a magnetic field and a protective magnetosphere. However, the magnetic field would have weakened as the small planet cooled and core convection ceased, leaving atmospheric gases vulnerable to being stripped into space by solar wind particles. So that's what this image here is trying to show. So Mars, way in the past, might have had this molten core, just like the Earth has, and that, along with the rotation of the planet, means that that liquid is convecting. Well, we see by that dynamo effect that a liquid electrically conducting fluid that's in motion can generate a magnetic field, kind of like a wire carrying a current. So the point is, Mars probably had a magnetic field and a protective magnetosphere around it. So whenever we had the solar wind coming in, those energetic particles would hit the magnetosphere and be diverted away from the planet. So Mars was shielded. But because Mars is smaller than the Earth, it means it cooled more quickly than the Earth. So that molten core probably solidified. Well, if you lose that molten core, well, then you don't have that fluid anymore to create a magnetic field. So Mars lost its magnetic field, and then the solar wind could come in and strip away much of the atmosphere. So that gives the general overview. With regard to water, although some lies frozen in the polar caps and underground, much of the water once present on Mars is probably gone for good. Like the carbon dioxide, some water vapor may have been stripped away by the solar wind. However, Mars also lost water in another way. Because Mars lacks an ultraviolet absorbing stratosphere, like we have on Earth because of the ozone layer, atmospheric water molecules would have been easily broken apart by ultraviolet radiation. The hydrogen atoms that broke away from the water molecules would have been lost rapidly to space through thermal escape. With these hydrogen atoms gone, the water molecules could not be made whole again. Initially, oxygen from the water molecules would have remained in the atmosphere, but over time, this oxygen was lost too. Some was probably stripped away by solar wind, and the rest was drawn out of the atmosphere through chemical reactions with surface rocks. This process literally rusted the Martian rocks, giving the planet its distinctive tint, that being a reddish-brown color. So, Mars is a red planet, literally because the surface is rusted due to ultraviolet radiation coming in and stripping away the water molecules, where oxygen then gets locked into the rocks and rusts the surface. So, Mars is literally rusted. Summarizing these ideas, we conclude that Mars's fate was shaped primarily by its relatively small size. It was big enough for volcanism and outgassing to release plenty of water and atmospheric gas early in its history, but it was too small to maintain the internal heat needed to keep this water and gas. As its interior cooled, its volcanoes quieted and released far less gas, while its relatively weak gravity and the loss of its magnetic field allowed existing gas to be stripped away into space. If Mars had been as large as Earth, so that it could still have outgassing and a global magnetic field, it might still have a moderate climate today. Mars's distance from the Sun helped seal its fate, though. Even with its small size, Mars might still have had some flowing water if it were significantly closer to the Sun, or the extra warmth could help melt the water that remains frozen underground and at the polar caps. The history of the Martian atmosphere holds an important lesson for us on Earth. Mars apparently was once a world with a moderate temperature, with streams, rains, glaciers, lakes, and even possibly oceans. It had all the necessities for life as we know it. But this once hospitable planet turned into a frozen and barren desert just 3 billion years ago, and it is unlikely that Mars will ever again be warm enough for its frozen water to flow. Any life that may have existed on Mars is either extinct or hidden away in a few choice locations, such as in underground water near not quite dormant volcanoes. But as we consider the possibility of future climate change on Earth, Mars does present us with an ominous example for how drastically things can change. And speaking of a drastic example for us on Earth, now let's talk about Venus. It's closest in size to us, so maybe it can tell us a little bit about what things might be like. Venus presents a stark contrast to Mars, but it is easy to understand why. Its larger size allowed it to retain more of its internal heat, leading to greater volcanism. The associated outgassing released the vast quantities of carbon dioxide that create Venus's strong greenhouse effect. Venus becomes more mysterious when we compare it to Earth. Because Venus and Earth are so similar in size, we might naively expect both planets to have similar atmospheric histories. Clearly, however, this is not the case. In this section of the lecture, we'll explore how Venus's atmosphere ended up so different from Earth's, and in the process, we'll learn an important lesson about the habitability of our own planet. If you stood on the surface of Venus, you'd feel a searing heat, hotter than that of a self-cleaning oven, and a tremendous pressure, 90 times greater than that on Earth. For example, a deep-sea diver on Earth would have to go nearly 1 kilometer or 0.6 miles beneath the ocean's surface to feel a comparable pressure. Venus's atmosphere consists almost entirely of carbon dioxide. It has virtually no molecular oxygen, so you could not breathe the air even if you cooled it to a comfortable temperature. Furthermore, moving through the thick air near Venus's surface would feel like a cross between swimming and flying. Its density is about 10% that of water. Looking upward, you'd see a perpetually overcast sky, with only weak sunlight filtering through the thick clouds above. Because the thick atmosphere scatters nearly all the blue light away, the dimly lit sky appears reddish-orange in color. The weather forecast for the surface of Venus today and every day is, well, quite dull. Venus's slow rotation, that is 243 Earth days, means a very weak Coriolis effect. As a result, Venus has little wind on its surface and never has hurricane-like storms. The top wind speeds measured by the Soviet Union's Venera landers were only about 6 kilometers per hour. No rain falls because droplets that form and fall from the cool upper atmosphere evaporate long before they reach the ground. The weak Coriolis effect also means that Venus's atmosphere has just 2 large circulation cells, much like what Earth would have if rotation didn't split up into those many cells that we see today. The thick atmosphere makes the circulation so efficient at transporting heat from the equator to the poles that the surface temperature is virtually the same everywhere. The poles are no cooler than the equator, and night is just as searingly hot as day. Moreover, Venus has no seasons because it has virtually no axis tilt, so temperatures are the same year-round. The weather, however, is much more interesting at high altitudes. Strong convection drives hot air upward high into the troposphere, where the temperature is about 400 degrees Celsius cooler than on the surface. Sulfuric acid condenses into droplets that create Venus's bright reflective clouds. The droplets sometimes fall through the upper troposphere as sulfuric acid rain, but they evaporate at least 30 kilometers above the surface. Moreover, high-altitude winds circle the planet in just 4 days, much faster than the planet's 243 Earth-day rotation. No one knows why these fast winds blow, but they are responsible for the dynamic cloud patterns visible in the photograph on the right. Speaking of, this composite image from the Venus Express spacecraft actually combines a visible wavelength image of the day side, which is on the left, shaded in red, and an infrared image of the night side on the right, shaded in blue. Venus's south pole here lies at the center. At most wavelengths, the clouds completely prevent any view of the surface of Venus. It's tempting to attribute Venus's high surface temperature solely to the fact that Venus is closer than Earth to the Sun. But Venus would actually be quite cold without its strong greenhouse effect, because its bright clouds reflect much more sunlight than we have reflected on Earth. The real question is why Venus has such a strong greenhouse effect. The simple answer is that Venus has a huge amount of carbon dioxide in its atmosphere, nearly 200,000 times as much as in Earth's atmosphere. However, a deeper question still remains. Given their similar sizes and compositions, we expect Venus and Earth to have had a similar level of volcanic outgassing, and the released gas ought to have had about the same composition on both worlds. So why then is Venus's atmosphere so different from Earth's? Well, we expect that huge amounts of water vapor and carbon dioxide should have been outgassed into the atmospheres of both planets. Venus's atmosphere does indeed have an enormous amount of carbon dioxide, but it has virtually no water. Earth's atmosphere has very little of either gas. So we conclude that Venus must have somehow lost its outgassed water, while Earth lost both water vapor and carbon dioxide. But how are these gases lost? Well, we can easily account for the missing gases on Earth. The huge amounts of water vapor released into our atmosphere condensed into rain, forming our oceans. In other words, the water is still here, but mostly in liquid form rather than gaseous form. The huge amount of carbon dioxide released into our atmosphere is also still here, but it's in solid form. Carbon dioxide dissolves in water, where it can undergo chemical reactions to make carbonate rocks such as limestone. Earth has about 170,000 times as much carbon dioxide locked up in rocks than it does in its atmosphere, which means that Earth does indeed have almost as much total carbon dioxide as Venus. Of course, the fact that Earth's carbon dioxide is mostly in rocks rather than in the atmosphere makes all the difference in the world. If this carbon dioxide were in our atmosphere, our planet would be nearly as hot as Venus and certainly be uninhabitable. We are left with the question of what happened to Venus's water. Venus today is incredibly dry. It is far too hot to have any liquid water or ice on its surface. It is even too hot for water to become chemically bound in surface rocks, and any water deeper in the crust or mantle was probably baked out long ago. Measurements also show very little water in the atmosphere. Overall, the total amount of water on Venus is about 10,000 times smaller than the total amount of water on Earth, a fact that explains why Venus retains so much carbon dioxide in its atmosphere. Without oceans, carbon dioxide cannot dissolve or become locked away into carbonate rocks. If it is true that a huge amount of water was outgassed on Venus, it somehow has disappeared. The leading hypothesis for the disappearance of Venus's water invokes one of the same processes thought to have removed water from Mars. Ultraviolet light from the sun broke apart water molecules in Venus's atmosphere. The hydrogen atoms then escaped to space, ensuring that the water molecules could never reform. The oxygen from the water molecules was lost into a combination of chemical reactions with surface rocks and stripping of the solar wind. Venus's lack of a magnetic field leaves its atmosphere vulnerable to that solar wind. Of course, Venus could have lost all of this water only if it had been in the atmosphere as long as water vapor. I'm sorry, let me re-say that. Of course, Venus could have lost all this water only if it had been in the atmosphere as water vapor, where ultraviolet light could break the molecules apart, rather than in liquid oceans like the water here on Earth. Our quest to understand Venus's high temperature therefore leads to one more question. Why didn't Venus, like Earth, end up with oceans to trap its carbon dioxide into carbonate rocks and prevent its water from being lost into space? Well, to understand why Venus does not have oceans, we need to consider the role of feedback processes. That is, processes in which a change in one property amplifies, which we consider a positive feedback, or counteracts, a negative feedback, the behavior of the rest of the system. With the idea of feedback in mind, let's consider what would happen if we magically move Earth to the orbit of Venus. So let's move Earth up a little bit. The greater intensity of sunlight would almost immediately raise Earth's global average temperature by about 30 degrees Celsius to about 113 degrees Fahrenheit. Although this is still well below the boiling point of water, the higher temperature would lead to an increased evaporation rate of water from the oceans. The higher temperature would also allow the atmosphere to hold more water vapor before the vapor condenses to make rain. The combination of more evaporation and more capacity for water vapor would substantially increase the total amount of water vapor in Earth's atmosphere. Now, remember that water vapor, like carbon dioxide, is a greenhouse gas. The added water vapor would therefore strengthen the greenhouse effect, driving temperatures a little bit higher. The higher temperatures, in turn, would lead to even more ocean evaporation and more water vapor in the atmosphere, thus strengthening the greenhouse effect even further. In other words, we'd have a positive feedback process in which each little bit of additional water vapor in the atmosphere would lead to a higher temperature and then even more water vapor. This process would rapidly spin out of control, resulting in a runaway greenhouse effect. The runaway greenhouse effect would cause Earth to heat up until oceans were completely evaporated and the carbonate rocks had released all their carbon dioxide back into the atmosphere. By the time the runaway process was complete, temperatures on our moved Earth would be even higher than they are on Venus today, thanks to the combined greenhouse effects of carbon dioxide and water vapor in the atmosphere. The water vapor would then gradually disappear as ultraviolet light broke water molecules apart and the hydrogen escaped into space. So, in short, moving Earth to Venus's orbit would essentially turn our planet into another Venus. So, we have then arrived at a simple explanation of why Venus is so much hotter than Earth. Even though Venus is only about 30% closer to the Sun than Earth, this difference was critical. On Earth, it was cool enough for water to rain down and make oceans. The oceans dissolved carbon dioxide, and chemical reactions locked it away in carbonate rocks, leaving our atmosphere with only enough greenhouse gases to make our planet pleasantly warm. On Venus, however, the greater intensity of sunlight made it just warm enough that oceans either never formed or soon evaporated, leaving Venus with a thick atmosphere full of greenhouse gases. So this is a great point to, I think, stop on this video. And in the next video, what we'll do is we'll discuss Earth's atmospheric history. We'll discuss what we are currently doing with our atmosphere, and then what future effects we might have on it. And this includes a bit of climate change discussion. So now that we know what happened to our two closest neighbors in the two extremes on Mars and Venus, we're already getting a better idea of how important these things are. So now let's shift our focus to Earth and study what's going on there. So that'll be in the next video. But for now, thanks for watching and have a great day.